In this video, we'll be dealing with applications of first-order differential equations in electrical circuits. In a circuit containing resistance R in ohms, inductance L in henries, and electromotive force E of t in volts, the differential equation L di dt plus R times I is equal to E of t models the amount of current I of t in amperes. This is the sum of the voltage drop across the inductor L di dt and the voltage drop across the resistors R times I equal to the voltage E of t. Both L and R are constants. The current I of t is called the response of the system. Let's have an example. A 12 volts battery is connected to a series in which the inductance is 1/4 Henry and the resistance is 6 ohms. So we should determine the current I of t if the initial current is 0. So we have the differential equation of 1/4 di dt plus 6 times I, which is equal to 12. So we have a linear first order differential equation. So multiplying both sides by 4 to have its standard form. So we have di dt plus 6 times 4, which is 24i, and 12 times 4 equal to 48. We're going to solve this using the integrating factor where mu of t is equal to e raised to the power of 24 dt. So our integrating factor is equal to e raised to the 24t. So we will multiply both sides here by our integrating factor e to the power of 24t. So we have e to the 24t times di dt plus 24 times e to the power of 24t times I equal to 48 e to the power of 24t. Using this technique, the left side of the equation is just equal to the derivative of the product of the integrating factor and our function I. So we have derivative of e to the power of 24t times I is equal to 48 times e to the power of 24t. So let's integrate both sides with respect to t. So left side with respect to t. So our integral of the left side of the equation is just equal to e to the raised to the power of 24t times I. And to integrate the right side of the equation, we will let u equal to 24t du is equal to 24 dt, and du over 24 is equal to dt. So our integral now is equal to 48 over 24, the integral of e to the u du. So e raised to the power of 24t times I is equal to the integral of the right side of this equation, which is equal to 48 divided by 24 is equal to 2 times e raised to the power of 24t plus our constant c. So to find I in terms of t, let's divide both sides by e to the power of 24t. So we have 2e to the power of 24t divided by e raised to the power of 24t plus c divided by e to the power raised to the power of 24t. We have I in terms of t is equal to 2 plus c times e to the negative 24t. To find the constant c, we will use the initial condition given, which is I of 0 is equal to 0. So we have 0 is equal to 2 plus c, since e to the 0 is equal to 1. So our constant c is equal to negative 2. So our function I of t is equal to 2 minus 2 times e raised to the power of negative 24t. So this is our current in all time t.